Here we go. Let's imagine we've got some object here that has a round profile. Could be a sphere, could be a disk, something like that. Let's just imagine we've got something that looks round from the side, and it's got a mass m and a moment of inertia I, and a radius capital R. We've put it on an incline of an angle theta relative to the horizontal, and we're going to define our axes as x down the incline and y perpendicular to the incline. So what forces do we have acting on our object? Well, we'll have the weight, and the weight acts straight down, so mg. For the time being, we'll assume that the weight can act at the center of mass. Actually, that's the way it works. So the weight acts at the center of the object. There's going to be a normal force, and the normal force will act perpendicular to the incline, like that. And then we know there's got to be some friction acting on the wheel. If there were no friction, it would just slide down the incline, just like a point mass like we've looked at before. In order to make it rotate, there's got to be some friction on it. That particular kind of friction is rolling friction, but it acts, as far as we're concerned, kind of like static friction. So I'll just call it static friction. That friction is going to act at the point of contact. And in what direction is going to act? Well, the wheel is going to try and roll down this way. The frictional force is going to be in that direction, F sub s. Okay? All right, there we go. Now, let's look at some equations of motion. We know that for the rotational motion, the torque is going to be equal to, well, what creates a torque? The normal force creates no torque. It goes right through the rotational axis. The weight creates no torque. It goes right through the rotational axis. But the frictional force will create a torque. So Rf for the torque, we've got R, which is the radius of the wheel, times the force, which is the frictional force. That's the net torque acting on the wheel. We know that must be equal to I alpha, so this equals I alpha. And we can then say that the frictional force is equal to I alpha over R. Okay, there we go. Now let's look at the translational motions. What forces are going to be accelerating the wheel down the incline? Well, we're going to have to break down our weight. So if this is, remember, if that's theta, this is theta. And this is the force acting down in the x direction. We'll look at the forces, so this is the translational motion. We'll look at the forces in the x direction. This will be mg, mg sine theta. Sine theta. So the forces acting down the incline are mg sine theta. And then the frictional force is acting up the incline, so minus fs. The normal force is only in the y direction, not in the x direction, so that doesn't get included in f sub x. This then must equal ma in the x direction. In other words, the acceleration of the center of mass. Okay, well, what do we have? We've got basically two equations. This one is turned into this one, so we've got this equation, we've got this equation, but we've got three unknowns. Let's imagine that we know m and I. Let's imagine we know those. What don't we know? Well, we don't know f sub s, we don't know alpha, we don't know a. But let's apply the condition of rolling without slipping. Let's assume that this is going to roll without slipping. So in that case, we can say that the acceleration of the center of mass, in other words, a sub x, is equal to R alpha. That's our condition for rolling without slipping. Now we've got three equations, 1, 2, 3, and we can solve them. Well, what do we get? Let's take this one here. We've got mg sine theta, minus fs. Fs is I alpha over R, minus I alpha over R, and alpha is A over R. So we'll have AX over R squared. And that must equal MAX. MAX. There we go. So now we've only got one unknown, assuming we know the mass and the radius and the moment of inertia. Bring this over here, factor off a sub x, divide by the I over r squared, and what do we end up? The m plus I over r squared, and what do we end up with? Let me just erase some of this and I'll put the answer down. Once we solve for a, we get that a is equal to mg sine theta divided by m plus I over r squared. And if we think about this, this kind of makes sense. mg sine theta, we know that that is the force acting down the incline. We've seen that when we were looking at blocks sliding down frictionless surfaces. The force down the incline was mg sine theta, the component of gravity down the incline. We take that and we're dividing by m plus I over r squared. This is basically the inertia that something has to being moved. But now it's got two parts, because not only is it translating, not only is it rotating, but it's translating and rotating. M is the inertia that it has to being translated. I over r squared, in terms of the linear motion, that's the inertia that the object has to being rotated. The bigger I, the harder it is for the object to be rotated. The bigger m, the harder it is for it to be translated. And combining these gives us the total inertia of the object to move down the incline with translation and rotation. Well, very, very good. So that kind of makes sense. Now, one thing we have not talked about, and it's a very, very important difference between translational motion and rotational motion. How do we talk about the directions of these things? We know that r and v and a and f are all vector quantities. So far, we have not talked about the vector direction of theta, omega, alpha, tau. We know that momentum as well is also a vector. P is a vector. What about L? Is L a vector? How do we talk about the directional properties of those quantities? Well, let's take a look at that. When we defined these translational quantities, we realized immediately that they were vector quantities because there were directions to these motions. And we could define very similar motions in different directions, which were very different sorts of things. For example, we could have a velocity of an object moving this way, or it could move this way, or it could move this way, or something like that. Those are very different kinds of motions. They're all velocities, but the directions are very different. We could have different positions. Well, positions depend on the coordinate system, but changes in position, something could go move this way, change in position this way, a change in position this way, change in position this way. Accelerations, obviously accelerating differently. Also, it can accelerate downward due to gravity. It can accelerate sideways, speeding up. Due to forces in different directions, I can push on this thing this way, or I can push on the wall that way. Momentum, obviously, all have different directions. What about these quantities? Do they need directions? Is there a different way that something could rotate through an angle theta? Is there a different way that it could be spinning with some different angular velocity? Well, yeah, very simply. We can imagine, say, my calculator here, and this calculator could rotate this way, or it could rotate that way. But that's a pretty simple difference. We could just define, say, this one is positive and this way is negative. That would be pretty easy. But what about if I rotated it this way or this way? Well, those are very different rotations than rotating it this way. How are we going to describe those? How can we differentiate one from another? Well, let's go back to the wheel. Okay, so let's imagine this wheel is spinning. How can we describe this direction? Well, if we look at a point over here, the direction of the motion is up this way. So could we describe this as a rotation going upward? Well, no, not really, because the point over here for the same rotation is now going downward. Those are in opposite directions. Up here it's going this way, here it's going this way. So how can we define a vector direction for this motion? Well, one thing that is consistent with all of this rotation is the axis of rotation. So this axis here. So maybe by defining the axis of rotation, what's the direction of the axis of rotation, that would allow us to say the rotation, be able to describe the rotation for the whole thing. But we've got one ambiguity. Do we want to use this part of the axis or the axis of rotation that's back here on this side of the rotation? Well, we're going to use a particular method of defining the direction, which is a little unfair to a large part of the population. But the rule that we're going to use, and I'm sorry about this, you'll see who I'm sorry to in just a second. The rule is called the right hand rule. So you can imagine this was developed by someone who was right-handed. But to be honest, later on there are advantages for left-handed people when they use the right-hand rule. I'll tell you about those when we get to them. So what this means is, what we're going to do is when we have something that's rotating, okay, imagine it's rotating, and let's imagine it's rotating this way. To determine the direction of the angular change, the change in the angular velocity, angular acceleration, if it's speeding up, let's start with omega. What's the direction of the angular velocity? Take your right hand, and you need to use your right hand. We'll see why in just a second. Curve your fingers in the direction of the rotation. So if it's going this way, I'm going to curve my fingers this way. In other words, you might say in a counterclockwise direction around the axis. So remember, here's the axis. I'm going to curve my fingers around the axis in a counterclockwise direction. My thumb then points in the direction of omega, which in this case is out of the board. So we need a way of describing the third dimension now. When we're talking about directions in the plane of the board, I can just draw arrows. I can draw an arrow that way, or I can draw an arrow that way. But when we want to describe directions that are perpendicular to the board, we need some new symbols. And we will use a circle with a dot in the middle and a circle with an X in the middle. The circle with the dot is like an arrow that's coming out of the board. So imagine there's an arrow coming out of the board toward you. What do you see if there's an arrow coming toward you? You see the point of the arrow. So this is the point of an arrow that's pointed in what direction? Out of the board. So this direction, a circle with a dot, means out of the board. Or if it's on a piece of paper, it means out of the page or whatever, perpendicular to the surface on which there's writing. So in this case, out of the board. Now, what is the circle with a cross on it? Well, it's easier to draw 4 than 3, but typically with 3 is what you usually will see. The 3 are the feathers or the fletching on the back of the arrow. So if you are looking at an arrow that's going away from you, you see the feathers or the fletching on the back of the arrow. And that's what this is. These are the feathers or the fletching on the back of the arrow. So this arrow is pointing away from you. So this direction is into the board. Or into the page or whatever. Into whatever the surface is there where the writing is. So we're going to use these two symbols to indicate directions when we're talking about directions that are perpendicular to our surface. So what does this mean then? When we have an object that when we're looking at it this way, it is rotating in a counterclockwise direction, we will define that as out of the board. Sometimes if we don't want to constantly put in unit vectors like x hat, y hat, z hat, we might just define this, we think of this as a positive rotation. Angles that are measured this way are positive angles. Angles that go the other way would be considered negative angles. In other words, rotations this way would be considered positive rotations. Rotations this way would be negative rotations. So what happens if we have something then that is rotating in a clockwise direction? Point our fingers in the direction of the rotation. In this case, clockwise, our thumb points into the board. And so this direction of rotation we would represent with the circle with the X in it. So this direction, the vector direction here, is out of the board. The vector direction here into the board. Now that's true for angles. As I said, angles measured this way, we would have a direction out of the board or a positive direction. Angles measured this way, we would say would be negative angles or have a direction into the board, rotations counterclockwise out of the board, rotations counterclockwise out of the board, clockwise into the board. What about accelerations? Well, accelerations will have kind of a direction similar to the way we had directions of acceleration for translational quantities. If we have a positive omega, or an omega in a counterclockwise direction that's speeding up, then we'll have an alpha out of the board. If we have a counterclockwise rotation that's slowing down, that would be an acceleration into the board. If we have a rotation that's clockwise, omega would be into the board. If it's speeding up, alpha would be into the board. If it's slowing down, alpha would be out of the board. So, when the, okay, so we'll leave it at that. We'll leave it at that for now. Okay, what about torques? How will we define the direction of the torque? All right, let's take a look.